So here we are. The preparation of organomagnesium compounds. As we all know, organomagnesium compounds are very special type of compounds. These compounds have a matter and an organic moiety. What makes this compound very interesting to us is that they can form carbon-carbon bonds. For example, let's take the carbon dioxide reaction reacting with our organomagnesium compound or Grignard reagent. The R group of organomagnesium compounds reacts with the R group of with the CO2 and forms the monocarbolic carboxylic acid, which on further reaction gives us ketone. That's not of concern. So here we are, the organomagnesium compounds. The organomagnesium compounds are the first metallic compounds to be discovered. Organometallic compounds. They were discovered by Victor Grignard in 1958, for which he received a Nobel Prize. They have been proved to be of great synthetic and analytic use. We can anal we have we can make alcohols, ketones. Let's come here. As we can see, we can make thiols. We can make thioesters. We can make simple alkanes, arenes, aliphatic compounds, vinyl vinyls, alleles, and aromatic compounds, simple hydrocarbons with this method. We can even make it using the alkyl halides as using copper as catalyst. Then even ethylene, which is a heteromolecule heterocyclic organic compound in which one of the C atom is replaced by another atom, which here is O, and this forms ethylene. 2C means ethane, and ethylene is just related to ethane. Now, as we are see that even it reacts with oxygen and forms carbon-carbon bond with oxygen. However, uh, peroxide group being very unstable, O is released and alcohol group is formed. It even reacts with nitrogen. So from our discussion we can see that it reacts with nitrogen, forms carbon bond with it. It reacts with sulfur, forms carbon bond with it. It reacts with any alkyl group, it reacts with any alkyl halide, particularly in which the alkyl which are electron withdrawing group. For example, the acetylene group, the b- phenylic group. Here we have the copper, which, as we all know, gives increases the rate of reaction. Now the Grignard reagent is prepared by reaction of alkyl halide with magnesium turnings. In this is a simple reaction, and I will give a link to preparation video which is very interesting. It is a simple reaction. We have a condenser, we have a simple flask in which uh, we add magnesium turnings, then dry ether, then we add alkyl halide solution, then we simply add iodine as a initiator. This is very spontaneous reaction, but in many cases, as we all know, the R group can be aromatic, can be allylic, can be vinylic, can be aliphatic. So they have different tendencies for the reaction. They they have different tendencies for the reaction, and if we take the example of aliphatic carbons, for example the CH3, it will be less reactive than C2H5, which will be in case less reactive than C3H7, and so on. This is because of the reason the breaking of the bond between the alkyl group and the halide group is the initiating step and rate determining step. This is the step which is needed, which must be done, and needs most energy. So for this rate determining step to occur, we add iodine, which reacts with magnesium and forms magnesium iodide, with which our alkyl halide reacts much more easily at a less threshold energy value. We can use dry ether, but in case of aromatic compounds and vinylic compounds, we use THF, tetrahydrofuran. This is because of the reason that tetrahydrofuran in actually coordinates with magnesium ion much better, forms a much better stable Grignard reagent, and shifts equilibrium towards the formation of Grignard reagent. So here we can see the rate of reaction with iodine is highest because we need less energy to break the bond between alkyl group and iodine group, then alkyl group and bromine group, then alkyl group and calcium chloride group. For a particular halogen, for example, if we take iodine, the methyl group will be much more easy to break. The C2H2 group, H5 group will be much less easy to break, and C2H7 group will be least easy to break among these three. This is because of the reason that these are groups are electron releasing groups, which as this order increases, as the number of carbon atoms increasing, they become much more electron releasing. They form a much more stronger polarized bond with this effect. The iodine, which requires more negative charge, attains more negative charge in the covalent interaction, gets stable, and they attain a positive charge. Due to resonance and other effects, this effect leads to much higher stability of bond. That's why our CH3 least electron releasing is the one having least energy needed to break the bond between iodine and CSC or any halogen and lead the reaction towards the position. So here we have there are the synthetic applications of Grignard reagent which I have explained earlier. We can make thioesters, we can make thiol coal. Now coming from the extreme left, there is thiol coal SH group. Simply we have to react with sulfur and it makes a carbon bond with sulfur and we have a thiol coal. Then we have a thiester. Simply dithiester is reacted with our given Grignard reagent and we obtain two uh, one thiol coal and a one thioester. Then we react we can react with alkyl halides it with any other alkyl halide which can give rise to particularly we react with vinylic alkyl halides and aromatic alkyl halides. This leads to equilibrium reaction between magnesium between organomagnesium compounds and alkyl halides. As we extract the alkyl halides or these get evaporated or these are obtained in the fraction, these get separated out of the solvent media, these more are formed. Then copper as a catalyst help in this reaction. Then it reacts with ethylene to form an alcohol having two carbon atoms much more than the R group of organomagnesium halide. Then it reacts with oxygen to form alcohol. First it forms a peroxide acid and then alcohol. Sorry, a peroxide alcohol and then alcohol. Then it reacts with imine, ketoamine, sorry. It reacts with the ketoamine and forms a tertiary alcohol. In this case, it is only forming bond with the carbon and it doesn't form any bond with the nitrogen. So we see the organomagnesium compound doesn't have the capability to form bond with the nitrogen, but it is very efficient in forming bond with the sulfur, oxygen, and carbon and extra. So, as I have explained, the alkanes are synthesized by reacting with alkyl halides, but in reality, there is another method which is much more useful is by reacting the compound which is having an active hydrogen. The active hydrogen is an acidic hydrogen. It has acidic properties because of H positive much more having on it. So if there are compounds such as alcohol, such as water, such as carboxylic acid, such as thiol, then we can have we react with Grignard reagent and in return this reaction gives us pure hydrocarbon and MgOH X whichever halogen we have used. So here is the reaction RMgX plus HOH. So the active hydrogen of acidic hydrogen of water is being given to RH plus Mg OHX is formed, which on further hydrolysis will give magnesium dihydroxide. So here we have an example. So here is the formation of aromatic compound benzene from an aromatic Grignard reagent. First, Grignard reagent organometallic compounds is the same thing. Victor, this was given in the honor of Victor Grignard, that all organomagnesium compounds will be called as Grignard reagent, whatever their function would be. So this ends. Hope you join my network. Stay tuned for further updates.